Our presentation is on the paper Tor, the second generation onion router. And the main author that we were looking into was Roger Dingledine. The paper presents the second generation of onion routing. New features include perfect forward secrecy, congestion control, directory services, new exit policies, and a redesign of the Tor hidden services. Onion routing is an overlay network that is built to anonymize traffic. Clients can choose a path in the network to build a circuit, and the traffic travels through the circuit, which is unwrapped by a symmetric key at each node in the layers of the onion. The traffic leaves the circuit through an exit node and goes to its intended destination. Many design issues with the version 1 routing were improved upon in the version 2 routing. In version 1, a malicious node could compromise traffic and force the other nodes in the circuit to decrypt the traffic. In version 2, they introduce a multi-layer encrypted data structure for the onion to protect privacy and security. Onion routing version 1 built a circuit for each app layer request, but this caused excessive key operations, which led to a higher threat in privacy. Version 2 multiplexes TCP streams for each circuit to improve efficiency and security. Version 1 had some speed issues because of bottlenecks and reckless users. So version 2 changed its congestion control, and it introduced a decentralized E2E acknowledgements for congestion control while maintaining the anonymous nature of the onion routing. Version 2 introduced directory servers. The initial implementation of version 1 flooded the network state information throughout the network. Version 2 chose to allow trusted servers to act as directory servers. Onion routing version 2 introduced end-to-end data integrity checks. By doing a check at the endpoints of the circuit, version 2 prevents hassle with regards to retransmission and security. Tor bases its work off projects such as Mixnet. Mixnet introduced the idea of wrapping messages in layers of public key cryptography. Some of the goals of the paper were to go over the deployment of onion routing. While onion routing protects privacy and security, deployment into the real world can run into problems such as the expenses from the volunteer servers. Usability. Using the Tor browser is fairly usable, but using other applications or creating other applications that run on the Tor network is fairly complicated. So the design they go over of the Tor network is they provide two definitions. So Tor is an overlay network with onion routers. So they abbreviate it to onion router to OR in the paper. And then each user runs an onion proxy, which they abbreviate to OP. And the proxy is used to create a circuit throughout the network for the users. Version 1 built a circuit for each TCP stream, where each creation can take 1/10 of a second because of the cryptography involved. Version 2 sped things up by allowing TCP streams to share circuits, which cuts down on the delay. The onion proxy considers rotating a circuit every minute. When opening a TCP connection, the request is sent to the onion proxy. The onion proxy chooses the newest open circuit. The onion proxy then chooses an onion router on the circuit to be the exit node. Once the exit node responds to the onion proxy, the TCP connection can be opened and commence with the onion proxy. Version 1 used streams without end-to-end integrity checks, which allowed traffic to be vulnerable to malicious intent. Integrity checks could happen at each hop by including hashes, but this introduces message expansion overhead. Checks at each hop also provide no protection against end-to-end timing attacks. Version 2 uses end-to-end encryption across the circuit. Versions 2 end-to-end integrity check incrementally adds to the SH1 digest with each relay. Each relay keeps the SH1 digest of the data received for verification. Volunteer servers can only provide so much bandwidth for free, and they don't want to overrun their volunteer servers with traffic, so Tor enforces a long-term average rate of incoming bytes. So with regards to congestion control, too many users on one onion router to one onion router connection can cause congestion, whether it's by malicious users or not. Each onion router keeps track of two windows. The package window, which tracks how many relay cells the onion router is allowed to package back to the onion proxy. The delivery window, which tracks how many data cells the onion router is allowed to deliver to TCP streams. Each of the cells is incremented with increments the window by 100, like similar to other congestion control mechanisms. If the package window reaches zero, the onion router stops responding to the TCP connection. The onion proxy tracks package windows and delivery windows for every onion router in the circuit. The hidden services. Hidden services can offer a web server without revealing IP addresses. Hidden services can prevent against DDoS attacks because the attacker won't know the IP address. Hidden services are providing several onion routers to contact for a client, and these several onion routers are usually stored within a distributed hash table. The client chooses an onion router from the distributed hash table, and then the client connects to one of the introduction points, informs them of which hidden service they should use. Each onion router exit policy describes external address and ports in which the router will connect. There is a range of exit nodes, from exit nodes that will connect anywhere, middleman exit nodes that relay traffic to other Tor nodes, and private exit nodes that only connect to a local host or network. So version 1 used routing which flooded its neighbors with its state. Version 2 uses a small group of well-known onion routers to track changes in the network and node states such as keys and exit policies. The directory server acts as an HTTP server where the clients can fetch the current network state and routing lists. If a directory server is compromised or attacked, the other directory servers use a majority vote to decide on onion routers, so the compromised directory server will not have an overwhelming influence. So the future directions that the paper points at are they have to handle scalability of the onion router because of the onion network, because it's been changing so fast. In 2004 there was less than 100 nodes, and now the network is massive and a lot more users. So there's been many scalability problems, and obviously using the Tor network and the Tor browser is going to have a lot slower performance at times than using a regular network. They've thought about implementing caching at exit nodes if users are requesting the same content all the time, then caching at exit nodes can speed up performance exponentially. They need to figure out some sort of way to provide incentives for volunteers to set up servers in the network, because not everyone will do it for free. And they just need to think about all the details of a wider scale deployment. And that's our presentation on Tor, the second generation Onion router by Roger Dingledine, Nick Mathewson, and Paul Severson.